Thank you, Francesco. Thank you very much to the organizers for the invitation and the opportunity to give a talk. So everything I'm going to say is joint work with Zheng Huang and Ben Lowe. And I will start by giving you a 3-minute teaser of the talk. So here's a theorem by Anderson in 83. So we give ourselves a Jordan curve lambda in CP1. We consider as the boundary at infinity of the hyperbolic tree space. So here's the picture of hyperbolic tree space, which is a ball. Its boundary at infinity. CP1. We take a Jordan curve, a C0 embedded curve, continuous. And Anderson theorem tells us that there exists in the interior of H3 a stable minimal disk a sigma in H3 such that its boundary, its asymptotic boundary, so the boundary of sigma in the boundary at infinity of H3 is the Jordan curve that we have given ourselves. So the picture is like that. There is a disk here, which is minimal. It's also stable. I will define these words. It fills the Jordan curve. Okay. And it's known, however, that this minimal disk is not unique. Sigma is not unique in general. Sometimes it is, sometimes it is not. So the questions that I want to address, the first question is, do we have some conditions, some criteria for uniqueness? So when is sigma unique? Okay. And the other question I want to talk about is when it is not unique, how many can we have? So how many solutions? These are the questions that I want to talk about. Well, for those who are interested in watching the actual movie, these are the characters. Let me give the definitions that appear in the theorem. I think everyone knows what the hyperbolic space is. So I won't define it. Let me tell you what a minimal disk is. So more in general, if we have an embedded surface in a tree manifold, surface, so we say that sigma is minimal if it is a critical point of the area under all compactly supported variations. So if the derivative of the area, derivative times 0 of the area of sigma t intersection k is 0 for every smooth family surfaces let's say sigma t with sigma times 0 equal to the initial sigma that we started with. And so the picture is something like this. We have a surface, and we want to say that if we vary this surface, sigma something which agrees outside the compact set, then the area of the original derivative of the area is 0. So sigma T intersecting K is equal to sigma intersection K, so compactly supportive variation. And it is known, and this is equivalent to the condition that H, which is the mean curvature, so it's the trace of the second fundamental form made with respect to the first fundamental form, is identically 0. This is the definition of. Oh, yeah, thank you. Thank you. Yes, yes, K is a compact, yes. K is something like this. Okay. Okay. Yeah, and the other definition, sigma is stable if, moreover, the second derivative is non-negative. Of sigma T intersection K is non-negative, okay? So this is, for instance, the case if our surface has the property that its area inside K is actually a minimum, which sometimes happens, sometimes it doesn't happen. In that case, it's called area minimizing, but I won't use it too much. So I will mostly stick to the stable condition, which is weaker. Okay. So examples. The first example is when our Jordan curve is just a round circle. Okay, lambda. Lambda is the round circle. In CP1. But then sigma is, so the solution sigma of this problem, this actually is theorem of Anderson. The problem it addresses is called the asymptotic plateau problem. So we'll talk about solutions to the asymptotic plateau problem. So sigma equal, the only solution is sigma equal to P, where P is the totally geodesic plane that has lambda as the boundary at infinity. So it is unique. This follows from the well-known fact that the surface is containing the convex hull of its boundary at infinity, and the convex hull is just a totally geodesic plane. So there's no room for more than one surface, and it's also stable. Okay, this is a very baby example. Second example I want to talk about is actually not an example of that theorem, but I will give it anyway, because it's interesting for what comes later. So let's consider this situation of two round circles. Okay, so this is again, here, this is not a Jordan curve because it's not connected, but let me talk about this example anyway. So let's take lambda equal to, let's say C1, disjoint union C2, Ci some round circles. Okay, so of course we can find a solution to the problem we're looking at by considering two totally geodesic planes. I'm saying a lot of triviality for the moment. So we have C1 and C2. So we can look at P1 and P2, and maybe we can say this is a solution to this problem in the sense that the boundary at infinity P1 union P2 is C1 union C2. But there is sometimes another solution, in the sense another minimal surface that appears that is now connected, namely something that looks like this, that is an annulus. Okay, but this doesn't always exist. But if the distance between P1 and P2 is less than some universal constant delta, So the distance between these two planes is basically the length of the common perpendicular between the two. Okay, if these two totally geodesic planes are close enough, then there exists what is called a minimal catenoid. Let's say sigma naught with the boundary at infinity of sigma naught is the disjoint union of these two circles. What is a minimal catenoid? It's let's say a minimal annulus, which is minimal annulus, which is obtained as a surface of revolution. So of revolution, where the axis is this common perpendicular. So we take basically a curve in a plane that goes through this axis, and we rotate the curve. And if the two circles are close enough, which maybe doesn't look like in this picture, but if they're close enough, then one can find such a thing. So with the axis is equal to the common perpendicular. As I said, this is not an example, so this is not convincing to say that there is not uniqueness in general, but there is this situation. And now this situation is useful to actually construct examples of non-uniqueness. Yes? Yes, the hyperbolic distance. If you want, this is really the infimum of the distance between pairs of points of P1 and P2. Yeah, you can. Of course, you can. Must be a formula which I don't know exactly what it looks like, but yes, I agree. Wow. Yeah. No, I don't think it really enters the argument, but it can be. Yeah, this condition can be equivalently expressed in several equivalent ways. I just prefer to stick to this one. But you're right. If you just want to look at the boundary, there's something that you could cook up just without looking at the interior, if you prefer. But for us, it's not essential. Okay. So now, third example. Now, I want to give an actual example of non-uniqueness. So I'll take a curve like that. It's piecewise smooth. We could make it smooth if we wanted, but it's not too important. It looks like this. Okay, this is our lambda. I will eventually need this band to be very thin and these edges to be very close, but I will explain this later. So the claim is that lambda, this lambda, is the asymptotic boundary of two distinct minimal disks. Let me draw a picture of how they look like. Just a topological picture for the moment. Anyway, I won't be able to draw any exact geometric picture. Okay. So topologically, the first one will look like this. So imagine that this is a roof. So I'm now drawing a disk, which is basically the ground of the upper level, together with the ceiling of the lower level. and we connect them by a band, by a little band here. Okay? So again, it's like we have a building, we are on the top, and we make this surface, which is the ceiling of the last floor, together with the ground of the roof. Okay? And the other one will look something like this. On the other hand, it will look like just sort of perimetral band. Okay, and the way that one shows that these two are actually different is by using minimal catenoids. So the thing is that we can put a minimal catenoid here, take two circles, one here and one here, and here is where I need these edges to be close enough so that basically I have this condition, so that I want these two circles to be close enough so that I can find a minimal catenoid here, okay? And I put another one here. Okay, and again, the band will need to be narrow enough and these edges close enough so that these catenoids actually exist. And then basically this disk will live in the complement of this catenoid, okay? Remember, this disk is basically ceiling and ground together with a little band here, so it stays in the complement of this catenoid, while here, this other one, which is just a perimetral band, clearly stays in the complement of a catenoid like that here, okay? And one can actually construct, so for the moment it's just a topological picture, but one can construct minimal disks, stable actually, in the complement, let's say sigma I equal to 1 or 2, in the complement of Ci, where C, this is C1, and this is C2, the complement, in the complement of one catenoid or the other one, okay? And these two minimal disks are different by some topological reason. So they're distinct. So what does it mean by topological reasons? Well, let me try to draw a picture. So basically what we can observe, we can draw a curve here, which basically is the core of the catenoid, together with all these the core of the band. And I can also draw another one, which is instead the core of this catenoid here, and then it goes like that. Okay? These two cores are linked. They look like that. These are linked. And this is the essential fact that allows one to show that these two disks must be different. So basically, because if they were equal, then we would have a disk with boundary the curve lambda. So then lambda would be null homotopic in C1 union C2 complement, which is not possible essentially because of this linkedness of these two curves. Okay, so this is an example of actual non-uniqueness in this theorem. Wait. And a fourth larger sources, much larger sources of examples comes from quasi-Fuchsian manifolds. Okay. Quasi-Fuchsian groups. So every speaker in the morning, Francesco, Roman, and Jean-Marc, all talked about quasi-Fuchsian manifolds. So we all know everything about them. So let me just, I will actually talk about quasi-Fuchsian groups. So what is a quasi-Fuchsian group? Let me first tell you what is a quasi-circle. So a Jordan curve, lambda in CP1, is a quasi-circle if lambda is the image of a round circle, so for instance, RP1, for a quasi-conformal map from CP1 to itself. Quasi-conformal. So a quasi-conformal map is basically a map that distorts the angle in a controlled way. It's not conformal, but the angle distortion is controlled. And a discrete group G, a group of isometries of H3, is quasi-Fuchsian if its limit set is a quasi-circle. So lambda G, what is lambda G? Is the set of accumulation points of orbits. Of G times x for some x in H3. These accumulation points are all at infinity. So this group is acting freely and properly. Sorry, and this is, I forgot to say, this is isomorphic to the fundamental group of a closed-oriented surface of genus at least 2. Genus at least 2. So we have a surface group which is acting freely and properly discontinuous on H3, and its limit set is a quasi-circle, a particular type of Jordan curve. And this is what gives in the quotient. So basically, this means that H3 mod G is a quasi-Fuchsian manifold. I will mostly talk about just the action of the group upstairs, but if you like to think about the quotient as it was done in this morning's talk, you can just think about the quotient. Okay, so there's two results that for uniqueness and non-uniqueness that are known in this setting. I will try to write them here. So non-uniqueness, then I'll need another word. For uniqueness results. And here I'll talk about uniqueness. Okay, so let me start by non-uniqueness. Here there is a theorem of Huang and Wang. For any natural number that exists a quasi-Fuchsian group G such that its limit set lambda G, which is a Jordan curve, it's a quasi-circle, is the asymptotic boundary of n stable and G invariant stable minimal disks. Okay, so in other words, in the quotient, we have n pairwise distinct, of course, stable minimal surfaces in this quotient manifold. But I prefer to think of it about something which lives upstairs and which is invariant by the action of the group. At least n, yeah. Thank you. Thank you. Okay. So this tells us that actually the uniqueness, the non-uniqueness can be quite strong. We can have an arbitrarily large number. On the other hand, there is a theorem by Uhlenbeck that gives us an important criterion for uniqueness. This is essentially Uhlenbeck, 83, always, okay. So if lambda is a Jordan, or let's say, well, yeah, if lambda is a Jordan curve, okay, let me write it like that. If G is a quasi-Fuchsian group, and there exists a G invariant minimal disk sigma with a boundary to infinity of sigma equal to the limit set, and an important condition that the norm of the second fundamental form of sigma is less than 2. So basically the norm of the second fundamental form of sigma is in general is the sum of the eigenvalues square, or the square of the eigenvalues of the shape operator, or the eigenvalues of the second fundamental form. Since the surface is minimal, the trace is 0, so h equal to 0 means that lambda 1 is equal to minus lambda 2. So basically this condition is just telling us that the eigenvalue lambda is absolute value is less than 1. Okay, so this is basically, in our case, this is 2 times lambda squared, where lambda is the eigenvalue. Okay, then sigma is the unique minimal disk, G invariant again, sorry, G invariant minimal disk with such asymptotic boundary. So in short, in the class of G invariant minimal disks, in other words, in terms of manifolds that descend to the quotient, if we have this condition on the norm of the second fundamental form, then we have uniqueness in this class, okay, among G invariant disks. And these are the two results that we have asked ourselves whether they can be extended without any group action. So the question that we addressed was how much of these results really works only for group actions, and how much the situation can be more general when we forget about group actions. Any question? Okay, so I give you our theorems. Okay, here just two remarks before giving our theorems. So about the non-uniqueness. So Anderson observed two things: that among G invariant disks, we can only have finitely many. G invariant. So in this setting, we can only have a finite number of G invariant disks. We cannot promote this to infinitely many. But you also have an example of countably many minimal surfaces with the boundary at infinity, a certain Jordan curve. Okay? He found an example of a Jordan curve that spans infinitely many but a countable number. Okay. So our theorem is that actually there are examples with uncountably many. So there exists a Jordan curve, actually quasi-circle, lambda, CP1, which is the asymptotic boundary of uncountably many stable minimal disks. Okay. And in the direction of uniqueness, write this here. I'm sure I have enough room. Okay, let's use a board here. Okay, so the theorem is that basically a generalization of this result without any group action. So if lambda is a quasi-circle and there exists a minimal disk sigma in H3 with the asymptotic boundary equal to lambda and the condition on the second fundamental form, where less than, actually we can do less than or equal to 2. Here, yeah, this was the squared norm of the second fundamental form, sorry. Then sigma is the unique minimal surface, not necessarily a disk actually, it's unique among also surfaces that might have topology, minimal surface with asymptotic boundary equal to lambda. No. So the norm for minimal surface, this is lambda 1 squared plus lambda 2 squared. This is 2 lambda squared. So this is less than or equal to 2. Basically, I'm saying that lambda is less than or equal to 1. Okay. So 1 is really has to be thought as the ambient curvature, basically. Or more precisely, you must think about it as the curvature of a horosphere. This is really sort of the threshold. Yes, that was my next remark. The remark here is that the condition, this condition of the second fundamental form, squared less than 2, this implies the sigma is stable. So under this condition, the surface is actually stable. But here I have uniqueness without any further assumption. It's not, if I have time to talk about the proof, I'll come back to this point. But uniqueness is in the class of any minimal surface, stable or unstable, disk or not disk, doesn't matter. Yeah, and I had a second remark for which I need some more space. Well, doesn't matter. Okay, I'll keep this. the other remark that I want to make here is that actually theorem 2 works under a weaker assumption that lambda is a Jordan curve, not necessarily a quasi-circle, of finite width. So what is the width? Let me draw a picture. We have a Jordan curve. We take its convex hull, as Roman and Jean-Marc were doing this morning, with this convex set. And the width of the curve is actually more precisely it's the width of this convex hull. So the width of lambda is defined as the supremum. So this is the convex hull of lambda. It has two boundary components. The lower boundary component. The supremum of the sum of the distance between any point in the interior and each boundary component distance. Lambda plus the distance between x and the other boundary component. Okay, where x varies in the convex hull of lambda. Okay, so is this again is the supremum of the distance between any point. The supremum of the sum of the distances between each boundary component. And this is a definition given by Bonsante, Denziger, Maloney, Schlenker. Okay, and they show that every quasi-circle has finite width, but the converse is not true. So there are Jordan curves of finite width which are not quasi-circles. So this is actually a more general assumption than the quasi-circle for lambda. Okay, any question? So I'll talk a little bit about the proof. I'll give some proof ideas of at least one of these two theorems. I'm not sure I will have time for both. Proof idea for theorem 1. So the idea is really to start with this construction. So remember, here we had a sort of building with its top, and we were looking at ceiling and ground. And now we want to do this, but for a building with infinitely many floors. So we basically, let me draw a picture in CP1 first. So that curve there in CP1 looks like that. Okay. Now we want to put infinitely many of these curves and connect them. So the picture will be something like that. We start by the same thing. Okay. Except that here we put some little band here, and we and also on the other side, and we do the same thing. So we something like this. Oh. And then we continue playing the same game, right? And so on and so forth. And also on the other side, a big circle like that, circle like that. Yeah. And then we keep going, okay? Okay. And we do it like we did before. We put these bands, we require them to be narrow enough and these edges to be close enough such that we have catenoids at every level, okay? And also some catenoids here. These circles can be made close enough so that we find a catenoid, okay? And we construct this curve, so lambda, we want to be invariant under homotopy. So let's say basically invariant by this transformation. Okay. And so this curve is a Jordan curve. It's easy. This is easy. Basically because, so when we do the next level, basically we're reducing the radius by a factor of 2. So everything is converging to 0. So if we had 0 and we add infinity to this curve, which lives in CP1, if we add 0 to infinity, this really becomes a Jordan curve. So the image of an S1, topologically embedded. And actually a quasi-circle. This is less obvious. I don't have the time to explain why, but uses a criterion by alphas. Basically compares lengths between 2 points and any third point which is contained between the two on the curve. I can tell you more about that, but I'll skip this part. Okay. And now let me draw the same picture, but the ball model. Okay. Now the Jordan curve looks like this one actually, except with infinitely many floors. Okay. So far it's exactly the same, except that we add a little band here, a little band below, and then we add another floor. Difficult to draw. And we keep going, all right? Oh, this was a mistake. And we keep going. I don't draw the back every time. We just draw the front. Then we keep doing like that. Now eventually it's going to convert to infinity, and the same thing here. And so on and so forth, it converges to 0. Okay? And remember, we have these catenoids. We have a catenoid that lives here before, and the catenoid that lives here. So the construction, so let me give a name to these catenoids. So this if we are on the nth floor, I call this CN0, and I call this CN1, okay? So the idea is one can construct for any choice of a function f from z to 0, 1, a stable minimal disk in the complement of the catenoids that are determined by this function. So in H3 minus the union over all j in z of the catenoid C, J, f of j. Basically, our function f at every floor chooses one of the two catenoids. And according to the choice, we construct a disk which basically looks like the disk we had before. So at every floor, depending on the choice, it might be either as before, ceiling and ground, ceiling of the lower level and ground of the above one, connected by a band, or if you made the other choice of the catenoid, it can be the perimetral band. Okay, and on the bottom we just connect by small bands here. So in the bottom we just connect all we have done by a little band that corresponds to this band that we have added. Okay, this is the topological picture. I have to show that one can make these to be minimal and to live here. But once we have these, they will be pairwise disjoint by the same argument. So, pairwise. So this is sigma f, let's say stable minimal disk, sigma f. So if f is different than f prime, then sigma f different than sigma f prime by the same reason. And so this gives us 2 to the power of z minimal stable. Disks. And these are uncountably many. I guess I have maybe less than 5 minutes, all right? Okay. So let me try to tell you very quickly what is the idea behind the proof of theorem 2. Where can I do this? Let's do it there. So proof idea of theorem 2. So let me try to tell you very quickly. I'll do it in 3 steps. So the first step is actually to look at what Uhlenbeck did. Uhlenbeck in the G invariant case. In the G invariant case, what Uhlenbeck observes is that if we have this condition of a stable disk, if we have this condition that the norm of the second fundamental form squared is less than 2, this implies that we can consider the sign distance function from sigma. Is it the sign distance? This is a function from H3 to R, a sign distance from the surface. This one has no critical points. Okay. And moreover, if we look at its level sets, so this is an equidistant surface. So the level sets equal to C has mean curvature of the same sign of C as C. So basically in a picture, if we move on this side, the mean curvature vector, which is H times the normal, is pointing inwards. So if we move here, it will be still pointing inwards. Now I'll give you the proof of Uhlenbeck just in words because I have no time. So Uhlenbeck says if we have another G invariant minimal disk, since this action of G gives a compact quotient, the sign distance on the second surface, sigma prime, must have a maximum. Okay? And in this maximum, this sigma prime should have vanishing mean curvature, but on the other hand, its mean curvature should be more than the mean curvature of this one because it's tangential. And this gives a contradiction. Okay? Now, this only works if really the maximum is achieved, which we can make if the quotient is compact. If we have no compact quotient, we don't have such an argument because the maximum might not be achieved. But if sigma prime is stable, we can use isometries and some compactness of stable minimal surfaces to reduce to the interior maximum case, minimum. So imagine we have now a maximizing sequence which is diverging. We use isometries to bring back to a compact region, take limits, and we will be again in this situation. This is because sigma is stable and also sigma prime is stable. Also sigma is stable because of what I said before. So now this gives uniqueness among stable. Okay, and the last step is the following proposition. That if lambda is a Jordan curve, and sigma is minimal, with boundary at infinity of sigma is lambda, then sigma is the unique so stable, let's say sigma stable. There is always one stable solution. So sigma is the unique stable minimal disk with asymptotic boundary equal to lambda, if and only if it is the unique minimal surface without any further assumption. Surface with asymptotic boundary of sigma equal to lambda. So uniqueness in the class of stable disks is the same as uniqueness in the larger class of all surfaces. So since we have proven uniqueness in the class of stable surfaces, then we have uniqueness in general. And yeah, I stop here. Thank you.